Hello students, so I'm back with another very interesting concept of the well-known neighboring group participation in an organic reaction. There are two separate questions that I'm taking up today, and you may say both of them are uh, affected by neighboring group participation. And do try the questions and pause the video and give it a try. I'm showing the questions now. So these are the two questions. The first one has an ether and with a benzene ring, and it is subjected to nitration, and the second one is a ring like this, and it is heated with water. I have given you the hint, and pause the video, give it a try, and we'll proceed with the solution now. So to proceed with the first part solution, we have been given this substrate, and this is subjected to nitration, and we know that in nitration the electrophile is NO2 plus. So an NO2 plus species approaches this molecule, and instead of the typical attack on the benzene ring, here we have an oxygen atom which contains a lone pair. So the first option for the electrophile would be somewhere which is an easier source of getting a pair of electrons, which in this case would be the lone pair of the oxygen atom. So the oxygen atom donates a lone pair, forming a coordinate covalent bond, and we get something like this with a formal charge on the oxygen. Now what happens is, when this further reacts or further proceeds on gentle heating, the attack of the electrophilic aromatic substitution occurs specifically from the ortho position. Why? Because this leads to the formation of a 6-member cyclic transition state, which can be drawn as you may do it like this, and yeah, so this is a 6-membered cyclic transition state, 1 2 3 4 5 6, and this is a transition state, and it proceeds to give the ortho product as the major product. So this case might be considered as a type of a neighboring group participation in the case of an electrophilic aromatic substitution. So let's proceed with the solution of the next question. Now in the next question, we have been given this substance, this reagent, this substrate, and it is reacted with H2O with some amount of heating. Now the first step that occurs is, due to the neighboring group participation, sulfur's lone pair attacks on this side, kicking out the chlorine atom, which is a sufficiently good leaving group, and it forms a transition state like this. The bonds have been given specifically in wedge, so this would be in wedge as well, and this is a formal charge. So this is its intermediate, and now when water attacks it, it has two options, either this or this side. These two are identical, you may say. Not identical, because if it attacks here, then it would form a 3-membered cyclic ring, so that is neglected already. And if it attacks here, or if it attacks here, if it attacks at site A, it would lead to the formation of the initial type of structure, which is 1 2 3 4 4-member ring, or in this case it can form a 1 2 3 4 5 5-member ring. So the 5-member ring would be favored, and therefore the attack for the major product would be from this side, and attacking by the H2O molecule followed by the removal of a proton, we get the compound as this. And as this is an SN2 attack, the attack would be from the dash position. So this is the final compound, which involved in the first step the neighboring participation of the sulfur atom, and then followed by an SN2 attack on the site which is most favored. So this is the major product, and we do get traces of a minor product of something like this. So these are the solutions of the